Oh boy. Because I found that word I would have been able to answer. But then as soon as I talked, I saw the message. I was like, oh, okay.
We're in the middle of 2.6. We're doing a little review of algebra in 2.6. What kinds of homework questions do you have before we continue on there? Did you have a question?
Just looking first, fill in the time at 2.4 with the UCP code.
Okay.
I just wanted to make sure that I was understanding it because, for example, when you have the missing digit for, I think it's Mindscape 15,
Okay.
you count that one as 3 and then the next one is 1, and the next one
Oh yeah. Yep. Okay, everybody be quiet for a minute, please, while we go over this Mindscape. So this first digit that's missing is going to get multiplied by 3. So when you figure out how much you need to add to your value, divide it by 3. Do you want me to do that example then?
Yeah.
Yeah. Okay, let's do that example. Okay, so we have a missing digit. I'll put a box. Okay. So as we write down the universal barcode with its missing digits, we have a box for the first one, which is the one that's times 3, and then it's times 1 times 3 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 times 1. So this time we have the check digit. It's a 9, but we don't have the first digit. So I'm going to put a question mark here. Okay, we don't know what that is. So the other ones, though, we keep our multiplying going here. And then check your multiplying. And then we add up those products. So what we want is for the total to come out to end in a 0, right? When you end in a 0, then you're a multiple of 10. So we want this total to come out ending in 0. Let's get the calculator and see what that adds up to. And you double check what you typed in your calculator. Make sure you type that in right. So this adds to 89. We needed to add to a number that's ending in 0. Now it couldn't be a 1 here because you have to have 3 times something. So it's got to be a multiple of 3. So not 1, not 11, because that's not a multiple of 3. How about 21? Okay, so if this was 21, 21 is evenly divisible by 3, so I'm going to pick 21 here. So if this is 21, then instead of 89, I'd have 89 plus 21, which is 110. So 110 is equivalent to 0 mod 10, okay, because 110 is a multiple of 10. So when you take out your multiples of 10, you take out 11 multiples of 10, and you get 0. So that means this number has to be 7. So I couldn't just add 1 on. That would get me to 90, which is 0 mod 10, but it's not a multiple of 3. So you have a little extra work on this one when you're not looking for the check digit, but instead you're looking for one of the digits in the middle. So we'll just check that. It should be 7 because I need to add 21 on. Let's just verify that. I think you all have different numbers, right?
So the check digits, it's just the same, except for instead of 3 times 1 times 3 is 7 3 times 9. It's the same.
Right, so when you're looking for the check digit, it's easier because then you just have to add in the number that gives you a multiple of 10. so that your total ends in a 0. You pick out the number here, and since it's just times 1, you don't have to do anything fancy like we just did. You don't have to backtrack and think about, well, how could it be a multiple of 3 also? You just, when you're finding the check digit, have to have the number between 0 and 9 that makes the total be a multiple of 10. Any other questions? So when you get to, using up 3 of your tries and it's not working out, feel free to send me a photo of your work, and then I can check and see what's going on, okay? So you don't lose your last try. Or stop by my office. Well, there were some questions about how do you upload photos in D2L when we're doing our Dropbox assignments. So if you go to D2L on your phone, you get this screen, which is frankly terrible. So don't keep that screen. Go to the bottom where it says desktop version and push that tab, okay? And then you'll be able to access the D2L Dropbox and your other aspects of D2L. Okay? And it'll be just like using your computer that way. Study group's going to be starting on Wednesday. It's going to be Monday, Wednesday, Friday from 2 to 3, starting this Wednesday. I haven't got a classroom yet, so I'll remind you again when I get a classroom given. We're going to continue on then in 2.6, looking at a little bit of review of algebra. Any more questions before we do that? Okay. So we're going to look at the prime factorization squared. So this will come up later on in the lesson, so we want to think about them now before it's part of a bigger problem. So when I have something like 136 squared, I don't have to take and multiply out 136 times 136 and then find the prime factorization. That would be a very big number. Instead, I can first find the prime factorization of 136. So remember how we do this. We start trying to see what divides into 136. Since 136 is even, I'll start with 2. (136) is 2 times 68. 68 is even, so I'm going to say 2 times 34. 34 is even, so I'll say 2 times 17. 17 is prime. So I have the prime factorization, 2 times 2 times 2 times 2 times 17. Well, that means the prime factorization of 136 squared is just the 2 times 2 times 2 times 17 times itself. So I just separated that product with parentheses, but of course you could just write 2 times 2 times 2 times 2 6 times and then 17 times 17 if you wanted. So when you have a prime factorization squared, you can just take the base, the 136, for example, find its prime factorization, and then multiply it times itself. So we never did see what 136 times 136 is as a number. We did not need to. Let's try another example. So if we're looking at the prime factorization of 75 squared, we would first just look at 75. It's more approachable, more doable. Now 75 is divisible by 5 because it ends in 5. So we'll work that out either in your head or in your calculator. It's 5 times 15. 15 is also divisible by 5. It's 5 times 3. And all these numbers are prime. So I have the prime factorization of 75. 5 times 5 times 3. So now to find the prime factorization of 75 squared, I just have to write that down times itself. So the prime factorization of a value that's squared, you can just go ahead and take the value you're squaring and find its prime factorization and multiply it times itself, and then you don't have so much work involved. Do you have any questions on that? Does anybody want to see another example? Okay, well, we'll see how that comes up later on today. For now, I want to review some fractions. Now, as we're working through this review, we have all different levels of math experience in here. Some people never did well in math and never liked it, and some people did great at math, think it's a fun topic, and are pretty good at it. So if those people who understand this review material are a little bored, I'm sorry. Please be patient while we get up to speed with everyone who doesn't remember it so well. So fractions, we can go ahead and think about what they are. So if I take one circle and divide it into 2, then I made 2 halves. Okay, so the denominator, the bottom of the fraction, tells how many pieces you're dividing one thing into. The denominator is on the bottom of the fraction, and the numerator is on the top. You can remember D for denominator, D for down. I don't have a good way to remember numerator, except it's not the denominator. All right. So the bottom of the fraction tells how many pieces you're dividing one thing into. So, for example, if you have fourths, then you're dividing one item into fourths. So here I divided the circle into 4 pieces. So fourths are smaller than halves, even though the denominator 4 is a bigger number than 2, because I'm dividing one thing up into smaller pieces. And then the numerator tells how many of those pieces you had. So for example, if we have 7/4, then we have 7 of these 1/4 of a whole. So we have 4 in one circle. Oh, that doesn't look good, does it? Oh dear. Pretend that's a better drawing. So we have 4 1/4 pieces and then another 3 1/4 pieces. So each of the fourths are 1/4 of a whole, and then there's 7 of them all together. So the numerator tells, or the top tells, how many of these pieces there are. Of course, you could write 7/4 as 1 and 3/4, because you have one whole and then 3 1/4 size pieces. Well, one of the things that we'll be interested with fractions is in reducing them. Do you have any questions before we look at reducing fractions? So take, for example, the fraction 2/4. So the 2 and the 4 are both even, so you could think of that as 2 times a 1 and 2 times a 2. 2 times 1 in the top and 2 times 2 in the bottom. Well, the fraction could be split up like that for the multiplying, instead of multiplying the numerator and denominator individually. And the reason you want to do that is because 2 halves is just 1. We already saw that on the first circle we divided. We took 1 and divided it into 1/2 and 1/2, or 2 halves. So this is just a 1. So when the top and the bottom of the fraction are the same, you're just looking at the value 1. And of course, if you take 1 and multiply it times anything, you have what you started with. So this is just a half. So that's reducing a fraction. You're just mathematically looking for the smallest number that divides into the numerator and into the denominator, and you divide that away, you cancel that out, because this common factor that's called, well, that is just a 1 when you divide it by itself. You can see that visually as well. If you take a 1/4, two of these 1/4s, you notice that that makes the same as a 1/2. So they're equivalent, just written different ways. So you can think of it visually with little fractional bits, or you can just do the algebra. 6/15, for example, what would you divide out of the numerator and the denominator? 3. Yeah, divide a 3 out. So you can think of that as a 3 times a 2 and a 3 times a 5. And the 3 divided by 3 is a 1. So we basically have 1 times 2/5, or 2/5. So a little bit of fraction review in reducing these fractions. Let's take a look at different kinds of numbers. We've looked at some numbers already, the natural numbers. Hopefully you remember what the natural numbers are. Can you please write those down? That's one of the things that you'll need to be able to do on the quiz, is write down several ways that we describe numbers, and natural numbers is one of those. So if you remember them, write it down. Anybody want to share what they wrote? Who remembers? What are those? Remember, they're the most natural feeling numbers for the ancient ancestors of ours. Yes?
Counting numbers, 1 to 2 to 3, 4.
Perfect. So the counting numbers.
Yeah.
1, 2, 3, 4, and so on.
And not negative.
Nope, not negative. Nope, in fact,
Ones you can see in nature, I guess.
that's very good. Ones that you can see in nature, and that's why they feel most natural. But saying the negatives made me think of integers. Does anyone know what the integers are? So that's a set of numbers we haven't talked about so far. Does anybody know what those would be? Integers are whole numbers. They have no fractional or decimal portion. So they do include negatives. So we'll start the dot, dot, dot to the left, meaning the negatives go on forever too. So dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. So that's a new set of numbers. I don't believe we've talked about them in our class today, up till today. Another set of numbers we have are the rational numbers. So I don't have an easy way for you to remember what integers are, but rational numbers have a word in them that can help you remember what rational numbers are. What word do you see in the word that can help you know what rational numbers are? Yeah, ratio. Good. So rational numbers are ratios or fractions. So we'll write a formal definition. Always want to know formally what definitions are so that we can be precise. Rational numbers are numbers that can be written A over B, where A and B are integers, and B is not 0. So informally, rational numbers are fractions, but formally we would say rational numbers are numbers that can be written as A divided by B, where A and B are integers, and B is not 0. We have a sign in the math suite, a big sign, and it says It's all fun and games until someone divides by 0. If you get mixed up that you can't divide by 0, just try it in your calculator. If you take out your calculator and divide by 0, you get a big error. Can't do that. Now the other way is all right. If you put 0 in the numerator, you have 0 divided by 5, that's fine. Boy, I'm glad that didn't go shooting off. What would 0 divided by 5 be? Does anyone know? Yeah, it's 0. Because then you're saying you have this circle cut into fifths, and you have none of it. Nobody shared their 1/5 of a pizza with you. Okay, so don't divide by 0, but 0 in the numerator is fine. Okay, so I'm going to give you some numbers, and I'm going to ask you to circle some of them. So we have 1, 5, 0.7, 3/5, and 0. I'd like you to circle all the rational ones, all the rational numbers. Circle all of the rational numbers in that list, please. Anybody want to tell what they circled? Yes.
0.73/5.
Okay, definitely 0.7, because that is, how would you write that as a fraction?
1/7. No, 7/10.
Perfect. 7/10. Yep.
Yeah, same.
And then the 3/5, that's a fraction. Okay. All right. Did anybody circle any others? So what you should have circled, and that's a good start, but what you should circle is all of them, because you can write them all as fractions. So if you're thinking, shouldn't I circle all these? Yes, you should circle all of them. So even if they don't start out life written as a fraction, if you can write it as a fraction of integers with no zeros in the denominator, then it is a rational number. We should look again at those decimals. How do you write something like 2.59 as a fraction made up of integers? Do you know how? No? Then you must not make eye contact. No, I'm just kidding. Does anybody know? Does anybody know how you do that?
Isn't it 259 over 1,000?
Almost. 259. And you pick as many zeros as you have decimal places. Yeah, 100. Good. So pick as many zeros as decimal places. $259 over 100. Well, we're looking at the rational numbers because the rational numbers are populous. They're populous, or they're dense. There's lots of them. There's lots and lots of rational numbers. And by dense, well, let's see what I mean by dense. Kind of like thick. They're like, well, here, let's show some examples. Find a rational number between 2/5 and 3/5. Let's find a rational number between 2/5 and 3/5. Well, one way to do this is to rewrite those 2/5 and 3/5 with larger denominators. So if you take that idea of reducing fractions and work it backwards, you can take your fractions and multiply each of them by 2/2, because remember that's just 1. But now I've written 2/5 as 4/10. We'll do the same thing with 3/5. Multiply that by 2/2. So you have 6/10. Now notice these are still the same. If you take 2 divided by 5 and compare that to 4 divided by 10, it's the same thing. Same thing with 3/5. 3 divided by 5 and 6 divided by 10, same thing. They're both 0.6. But now it's easier to see what would be a fraction that would be in between 2/5 and 3/5. What would be a fraction between 4/10 and 6/10? Yeah, 5/10. Yeah, so we got 5/10 there in the middle. Or 0.5. Yes?
It'll reduce to 1/2. So
Yes, and that reduces to 1/2. So if you want, you can write 1/2 down. Were you going to say something more? Okay, I'll say or 1/2. Good thinking there. Okay, well, we have the 2/5. Let's find a rational number between 2/5, but this time I'll write it as 4/10, and 5/10. So we'll narrow our search. Before we went from 2/5 all the way up to 3/5, and now we'll just go a little bit further, because now we're going between these two numbers, 4/10 and 5/10. But we could use the same approach. So let's use the same approach. Let's take each of these little fractions and multiply them by 2/2. So we have 8/20 and 10/20, and both of these are still what they started out. They're just written differently. So if you put in your calculator 4/10 and 8/20, both will come up as 0.4. If you put in your calculator 5/10 or 10/20, both will come up as 0.5. But now you can go ahead and find a fraction between 4/10 and 5/10, or between 8/20 and 10/20, and what would one fraction be? Yeah, good, 9/20. So we found a fraction between 4/10 and 5/10, and it was 9/20. Okay. So at your desk, find a rational number between 4/10, and now we'll have an even smaller location. Let's not write 4/10, let's write 8/20 and 9/20. So go ahead at your desk and find a rational number between 8/20 and 9/20, and you can use that technique that we just used. Yes. 17/40. I think so. You're ahead of me. Let me catch up. Nicely done, indeed. 17/40. So we started with two fractions, 2/5 and 3/5, and we found 1/2, which is 5/10, 9/20, and 7/40. They all lie between the 2/5 and the 3/5. So we have the 2/5, and then we had all three of these numbers fall in between that. I think the 17/40 would be closest, so I'll write that next. So we found all of these numbers that fall between 2/5 and 3/5. How many more were there? I mean, we stopped at 3, but how many rational numbers fall between fall between 2/5 and 3/5? Yeah, infinitely many. Good. Infinitely many, because we could have kept doing that forever, right? But it was fun, but it wasn't that fun. So 3 was enough to actually find. So that's why I said that the rational numbers are dense. They're populous. There's just clutters of them all over the place. In fact, the Greeks, namely Pythagoras, believed that all of the numbers were rational. So they tell us all numbers are rational, and we're going to see how the proof works when we go to prove that all numbers are rational. In other words, all numbers are fractions. So the Greeks were led, I say the Greeks, but I'm meaning Pythagoras and his cult, because really his disciples followed him, and it was more like a cult. Very weird, strange ideas. Besides the math, they had these other weird ideas with it. Maybe that's where mathematicians started being thought of as strange. Not sure. So the Pythagoras disciples tell us that all numbers are rational, and we're actually going to look at that proof. So we'll look at a particular number to prove that it's rational, and we'll get to it through the Pythagorean theorem. Who remembers what the Pythagorean theorem says? Did you have your hand up?
Are you asking like a squared plus b squared equals c squared?
Good, perfect. A squared plus b squared equals c squared, where c is the hypotenuse of a right triangle. Where C is the hypotenuse of a right triangle and A and B are the legs. The legs mean that they're the sides forming the right angle. So let's just go ahead and draw a picture. So a squared plus b squared equals c squared, where c is the hypotenuse of a right triangle. So we'll draw a nice right triangle. So we have a 90-degree corner here. And c is the hypotenuse, so it's the opposite side. So that makes c the longest side, and c has to be by itself in the equation because it's the longest piece. So it's the only one that's big enough to be by itself on one side of the equation. So we've talked a little bit about Pythagorean triples when we looked at Fermat's last theorem. And so we had an example of a 3, 4, 5 right triangle. So if A was 3, B was 4, and C was 5, then the hypotenuse would be the longest side, 5, and 3 squared plus 4 squared would be 5 squared. And in fact, you see that is true. Well, we're looking at a particular right triangle that the Pythagoreans considered. We'll look at the right triangle. That's the simplest right triangle, where the two legs are each 1. So we have a right triangle with one on one leg and one on the other. So A and B are both 1. And what we're going to do is look at c. So c squared equals 1 squared plus 1 squared. Well, 1 squared is pretty simple. It's just 1. So c squared is 1 plus 1. So c squared is 2. And then we can do the same thing to both sides of the equation. So the square root of c squared is the square root of 2. That means c is the square root of 2. So this is the simplest right triangle where the two sides are just 1. The two legs are just 1. And we want to go ahead now and consider this as Pythagoras did. We're going to prove the square root of 2 is a rational number. Prove the square root of 2 is a rational number. So there's a couple of proofs that I told you that we'll do throughout the semester, and this is one of those. Okay, so if you weren't taking notes, this would be a good time to start taking notes. So we're going to prove the square root of 2 is a rational number. Okay, so we're going to assume the square root of 2 is rational and see how that follows. So we're going to start making assertions about the square root of 2 that are irrefutable. So if the square root of 2 is rational, then the square root of 2 equals a divided by b, where a and b are integers and b is not 0. Where does that come from? We've seen that earlier today. Does anyone remember where we saw a over b are integers and b is not 0? Yeah, that's right. The definition of what a rational number is. So we're just quoting the definition back. If square root of 2 is rational, then this is in fact what's going on. Square root of 2 is a over b, where a over b are a and b are integers and b is not 0. So now we'll do a little algebra. Remember, whenever we do a little algebra to one side of the equation, we do the same thing to the other. First thing we'll do, multiply both sides of the equation by b. So where's my red pen? I'll multiply both sides by b. Now this is like a b over a 1, if that helps you think it through. So the b on the right divides away. You have b times the square root of 2 equals a. I'll show you why it divides away with a little example off to the side here. So suppose you had 2/5, and I multiplied that by 5 over 1. That's 10/5, which is 2. I don't know why I wrote the 2 so small. So the 5s actually just divide away. I didn't even have to write 10/5. I could just write here, have the 5s cancel, because that's what happens. The whole thing reduces by the 5. So that's what's happening with a b. The b is like a 5 and it's dividing away. And so that's why that's working. So we do the same thing to both sides of the equation, and that makes the b cancel on the right. And now we'll square both sides of the equation. So both sides are equal, so when you square both sides, the results are equal as well. So you have b times b is b squared. Square root of 2 times square root of 2 is 2. And a squared on the right. Well, now we have a little problem. This is a little problem. Let's go and see why is this a little problem. Remember when we looked at the 136 squared and the 75 squared? Where is that in your notes? So you have the 136 squared, and you have the 75 squared. That's like our a squared and b squared, okay? Just, those are specific examples of what a squared could look like or what b squared could look like. So notice a squared, 136 squared, you just took your prime factorization and multiplied it times itself. Same thing with the 75 squared. Took your prime factorization and multiplied it times itself. So here you have 8 prime factors of 136 squared, because you have 4 factors times 4 more factors. Or here you have 6 prime factors, because you have 3 factors times 3 more factors. Well, what we're seeing in those examples is that the number of prime factors, counting repeated factors, number of prime factors counting repeated factors appearing in a squared and b squared is even. The number of prime factors appearing in a squared and b squared is even. Okay, that's counting repeated factors. Since every factor occurs twice. So every factor that shows up in the factorization of 136 shows up twice when you have 136 squared. So you have the first 136 times the 136 again. So every factor is showing up twice, and that gives you an even number of factors. Again, okay, so the 2 is here, the 2 is here again. The second 2 is here, the second 2 is here. Third 2 is here, third 2 is here. 17 and 17. Every factor in a squared or b squared shows up twice. So you have an even number of factors. Why is that a problem? Does anybody see where the problems arise in here? Okay, let's keep going then. On the other hand, two b squared has an odd number of factors. Two b squared has an odd number of factors because there's the even number of factors from b squared, the b times b, so you have an even number of factors there. And then there's an extra 2. So there's an odd number of factors in the 2b squared and an even number of factors in the a squared. Why is that a problem? Yes.
Doesn't factor out maybe even.
Yeah, how could they be the same? How could they be the same? We say they're equal, but there's an even number of factors over on the right side with the a squared, and an odd number of factors on the left side, because there's an even number of factors from b squared, and then there's one more too. We'll say it more explicitly. We'll say by the fundamental theorem of arithmetic, I don't think there's extra either. Pretty sure there's not. Whoops. We have a unique factorization into prime factors. By the fundamental theorem of arithmetic, we have a unique factorization into prime factors. Okay, so unique meaning there's only one way to factor. There's only one way to factor a squared. There's only one way to factor b squared times 2. You can't have one prime factorization with even number of factors and one prime factorization with an odd number of factors be equal, because there is only one prime factorization. So two factorizations of the same number will have the same number of prime factors. Two factorizations of the same number will have the same number of prime factors. So if a squared is equivalent to 2 times b squared, the prime factorization will be the same for both. So they shouldn't be an even number of factors on one side when we factor a squared, and an odd number of factors on the other side when you factor b squared times 2. Okay, well this is the problem. Where did we mess up? They must have messed up somewhere, okay? Let's look and see. Remember, our proof should be infallible. We should have a number of steps to follow that come out exactly true. So we have assume the square root of 2 is rational. Then this is our definition, so we don't mess up there because we just copied the definition of what it means to be rational. Square root of 2 is a over b. We did the algebra right because we did the same thing to both sides of the equation. But we're coming down after we did the algebra to a squared equaling 2b squared, which we just saw can't be correct because there's even a number of factors on one side and an odd number of factors on the other. Does anybody see where the error is? Where did the error occur? Yes.
Is it the square cancels out the square root, or no?
Yep, it did cancel it out right there. So that square did cancel that. So we did that part right. Okay, so there's a square, and we squared it, and that square root's gone. So that's okay. That part we did okay. Does anybody see where the problem is? What happened? Where is there an error? There's definitely an error. Does anybody know where it is? Is anybody online going, I don't know. We'll find out. Here's where the error is. The square root of 2 is not rational. Their assumption is wrong. Ideas have consequences. We take our idea and we follow it through to its logical conclusion, and it is wrong. B squared, I can put the 2 on the left or the right, I'll write it on the left. B squared does not equal a squared. A contradiction. So the square root of 2 is not rational. So this was shocking to the Greeks. Here's a number that is not rational. Look how dense the rational numbers were. We could find infinite rational numbers between any two rational numbers, and yet here's a number that's not rational. This was so upsetting to the Pythagoreans. They had dire ramifications. Let me make this big enough so I can actually read it. The Pythagoreans reacted strongly to the disturbing discovery of irrational lengths or numbers, and they kept the idea secret. It is said that when one of their members was caught revealing the secret, he was taken on a boat ride and thrown overboard. Think we're joking? Proclus, around 5th century CE, gave a brief account. It is well known that the man who first made public the theory of irrationals perished in a shipwreck in order that the inexpressible and unimaginable should ever remain veiled. And so, the guilty man who fortuitously touched on and revealed this aspect of living things was taken to the place where he began, and there is forever beaten by the waves. Okay, so seriously, difficult idea for the Pythagoreans to grasp, that there are numbers that are not rational. I'd like to do one more proof that that's not so wordy with the square root of 3, so that you have an example that you can use that doesn't have so much verbiage in it. Hopefully the first proof will be here for you to understand and make sure you know it, but then we'll do one with a little less words. Because what I'd like you to be able to prove, of course, is that there are some numbers that are not rational, and the square roots of those numbers that are not perfect squares are in those irrational numbers. So a good quiz question would be to prove the square root of 3 is irrational. And we start by assuming the square root of 3 is rational. So we start by assuming the square root of 3 is rational, because then we'll have this contradiction that shows that it's impossible. Okay, so assume that it is rational, then the square root of 3 equals a over b, where a and b are integers, and b is not 0. So we're just going to our definition. So this gives us some algebra to work with, so here's where you would do the algebra. So multiply both sides of this little equation by b. And the b at the right-hand side cancels then. So you have the square root of 3 times b. You can put the b in front or on the after the square root of 3, either way, just so your b doesn't slide under the square root. So we multiply both sides of the equation by b, and then we square both sides. So when you square both sides of the equation, you'll have a 3 times b squared is a squared. And here's where you can say the conclusion then. The number of prime factors appearing in a squared and b squared is even. On the other hand, three b squared has an odd number of factors. An odd number of prime factors. So, a squared does not equal 3b squared. A contradiction. So the square root of 3 is irrational. So that's what I would expect to see on a quiz proof, and you can practice this a couple times before the quiz, because this isn't easy, and figure out what notes you need to put on your 3x5 card to help you do this. I'll see you on Wednesday when we'll start a new section.